Hey everyone, welcome to the start of our second half of our logarithms and polynomials series. As you can see from the title, we are going to be introducing polynomials in this video. And this will hopefully be a light introduction to you. And believe it or not, we've actually encountered polynomials for quite a few years now in your schooling, maybe just without knowing that this was their name. Now, there's this really kind of extensive definition of a polynomial that you'll see in your textbooks that I've included here. So it just says a polynomial is an expression of the form a to the sort of little subscript n, x to the power of n, plus a n minus 1, x n minus 1, etc. Right? We're just going to break this down. When people see this, they get really overwhelmed. We're just going to talk about the main key points, introduce some polynomials that we've actually looked at before, as well as decide if certain expressions are polynomials later in this video based on what we've talked about here. Now, all polynomials, essentially, there's some kind of expression with our x's to the power of something. Now, with all of these things that we have here, our n here that we have, for example, is going to be some whole number. So n is a whole number. So we can have x to the power of 0, x to the power of 1, x to the power of 2, etc. So they have to be whole numbers. Now, in this definition that we have, the other terms here, our things in front, so an, a to the n minus 1, all of these ones along here, these are what we call our coefficients. So things that we've sort of talked about quite a bit before, but we're going to see where this all sort of fits in. These are what we call coefficients. Okay, next, this thing, our a naught, x to the power of naught, is the constant term. Now, we've talked about constants way back in year 7 algebra. Our constant term is just something that doesn't have an x after it, or a y, or any kind of variable. It is a standalone sort of regular number. Now, applying what we basically know about index laws to this, which we've talked about before. Now, a naught is just some coefficient. It's just a number. So this can be something like, I don't know, 5. Now, x to the power of naught, our sort of last thing in this polynomial expression, this is a constant. Now, we always put our last number way back in algebra right as some kind of whole number or any other number right at the end. And the reason that's a number based on this notation we came up with is that x to the power of naught, any number to the power of 0 is just 1. So this is like saying a naught, some coefficient 5, times x to the power of 0. That gives us 1. So this would just be our 5 at the end of our expression. Right? So this is sort of now breaking down some of these dot points. But we'll leave that there. We're going to look at a few more later. And finally, we have our last definition is that a n x to the power of n is the leading term. In other words, the first term in our expression, and it will also have the highest power. Because think about it. If this is just any number, let's say it's 4, this is going to be 4 minus 1, 3. This is going to be 4 minus 2, 2, all the way down to 0. So when we write polynomials, we start with our highest power first, and then we go down in order of largest to smallest. Okay, so polynomials, they are named by the highest power of x. This is what we talked about before. Power of x. And this is also called the degree of the polynomial. So basically it tells us how extensive this kind of polynomial is. So we've actually looked at a couple of these before. Let's revisit some of them. So we talked about linear expressions, linear algebraic expressions. So for example, 2x plus 5. So you've got your leading term, my 2x to the power of 1, and we have our constant at the end here. If you look, this actually satisfies our definition of a polynomial. Now, you're probably thinking, well, what about all these numbers in the front, which are higher powers, because a naught x to the power of 0, our constant all the way down here, is just the second last term. So our other one here is going to be somewhere around here. These things still exist, but we can just think of that as just being 0. Because if you times 0 by anything, it's just going to eliminate it completely. So the only things we're focused on are to the sort of right-hand side of this definition, near our a naught, near our a naught x to the power of 0, as well as one of them over here. But linear expressions are types of polynomials. We've also looked at quadratics before. Quadratic expressions. Something like 3x squared minus 7x plus 11. This still follows our definition of a polynomial. It's got a leading term, it's got a constant, it's got a bunch of coefficients, and it's got the powers descending from the highest one. So this has a highest power of 2, and then it basically goes down. Couple more, we've talked about cubics before. Something cubed, let's say 6x cubed minus 2x squared plus 5x minus 8. We've talked about cubics before, and these go higher and higher and higher, all the way down to, let's just do another one like later on, a polynomial of degree 9. Now this would be something like, I don't know, 3x to the power of 9 minus 4x to the power of 5 plus 13. Now, we have once again our leading term, our highest power, and the powers basically go down. Now you may notice I'm missing some terms here. You're probably thinking, well, what about x to the power of 8? What about x to the power of 7? It's that same thing we were talking about up here, where these coefficients may actually be 0. So those different terms just don't show up. So these are the main definitions of our polynomials. Let's do a couple of examples to finish off today, talking about deciding if expressions are polynomials. So the first one is 4x squared minus 1 plus 7x to the power of 4. Okay? Now, the only thing we need, a main criteria for these polynomials, is are the powers of x whole numbers? Because remember, we said here that n is a whole number, 0, 1, 2, etc. So this thing, I mean, we can rearrange it so that the leading term is out the front, but we can pretty clearly see that all of these are whole numbers. And this can be, 1 times x to the power of 0, so it just disappears. But they are still whole numbers. So therefore, we can say that this is a polynomial. Okay, let's look at one more to wrap up today. 2x squared minus the square root of x plus 2 over x. Okay, this is a little weird. Now, we want to express this in terms of powers, right? We want to determine what kind of powers these two terms have of our expression. We know this one, that's all good. But let's write these ones I've highlighted in pink using index notation as x to the power of something. So we're going to stick with our 2x squared. Now, our surds, our square root of x, we've talked before that we can write this as x to the power of half. If you need to revisit this, I'm not going to do it now. We've talked about this extensively before, but we can write square roots as fractional indices. And finally here, my x is on the bottom here. We can write this as 2x to the power of -1. Because remember, when we have a negative power, we can bring that term down to the denominator. So let's look at the ones we have here. I can pretty clearly see that this thing here is definitely not a whole number. And for polynomials, we need to go basically up from 0. All of these go from 0 upwards. So we can't have negative powers when polynomials are concerned. So this thing also violates my definition of a polynomial. So this expression here is not the expression of a polynomial. Now that brings us to the end of the video today. We've just introduced polynomials, kind of tied them back to things we've talked about before: constant terms, linear expressions, or quadratic expressions, cubic expressions, ones that we've seen a lot in the past, but maybe just didn't realize that they fell under this umbrella, this family of polynomials. Now, in the next video, we're going to talk about some polynomial notation and a few other concepts after that.